So last time, basically this is sort of basic Lyapunov criterion. It's the sort of the crudest you can come up with for stability of Markov chains. And I gave you 3 ways of interpreting it. And remember, there was one really nice one that gave us transient bounds that I love. I mean, I'll write that down again. So I hope you all can appreciate why I like that so much, because I know it's a crude bound on cost. We're averaging over ensembles of realizations and over time, but it requires no conditions. But all we need is v greater equal to 0. So all Lyapunov functions are non-negative. That's the only thing required to go from here to here. And then I mentioned some other things too. And so there's also spectral theory. Which gave us an ergodic theorem. And wouldn't it be nice if these damn Jordanians didn't come to our country and introduce this decomposition? If all matrices were inverted, could be diagonalized, this world would be so much simpler. But I searched on Wikipedia, and actually it's Camille Jourdain from École Polytechnique in France. So no, I can't blame the Middle East. But it is too bad, that you can't diagonalize any matrix. You have to instead use a Jordan decomposition. But it's a very nice generalization of diagonalization. And so the fact that the eigenvalue result leading to, if you don't know it, if you haven't taken state space control, look it up. And the Jordan decomposition immediately gives you the ergodic theorem, once you understand the spectral theory. There are kind of a few holes in that, in my whole if and only if statements, but we'll patch up the missing holes in the next week or so. Let me think. Now, as I was saying to Aditya when we walked together in today, this is a real balancing act, because I know you're not in here to get a degree in mathematics, yet there's mathematical foundations that are really useful if you want to do anything. In fact, I might make Aditya show you all his recent numerical results, which could never have been obtained without a deep understanding of some of the concepts in this course. But I have to be careful in choosing which ones are really essential and which ones are not. And so this was one, I should write. Okay, so actually, let me say again. So Poisson's inequality gave us a bound on the average cost, averaged over time and on realizations. There's also this notation I brought in, which I hope you all digest. Pi of c, which is a dot product. If you follow our, it's a steady state mean of a cost function c. That's bounded by eta bar. What is not clear here is bounds on value functions. So we've got discounted cost value functions. We've got this Poisson equation, which we'll see as a value function. And we need bounds on these for, I mean, we need to understand them in order to develop algorithms, you know. So I'll go through and explain this. So that's basically today. But my defensive tone is that I want to teach you some math, you know, that maybe is a little bit more than you want to hear. And so that sounds like a lot for one lecture. And I have to, you know, again, I have to really think, do I really need to dump so many concepts in a course for which many of you just want to get an algorithm and run? But if you just want an algorithm and run, just go to Wikipedia, you'll see the algorithm for Q-learning, and you'll see it doesn't work at all. It's just completely horrible, and you'll see. And by the end of this course, you'll know why. You know, it's just completely flawed. Its conception was just a bad. So Watkins, who created it was brilliant, you know, but he didn't have the statistical tools to do better. Okay, and now we do, you know. And so I want you to get the, you know, I want to pass on this wisdom to all of you. And I wouldn't do it if I didn't believe it was valuable. Okay. Martingales, a lot of you interested in reinforcement learning, the entire analysis is based on martingales. The only way you get convergence is understanding martingales. I couldn't possibly not tell you about this, so why not start early? The strong Markov property, is it essential to your life? No, but it's not that hard to talk about, you know. And stopping times are essential to everything. I mean, they come up everywhere, and not just in Markov theory. So, so let's do it. But so first of all, again about goals. Like, for example, so this is what we call Poisson's equation, and here this is a discounted version. And if you don't like the fact I'm using it, obviously these are different functions, but in finance, oh wait a second, I've got this wrong, don't I? No, that's right, no, that's right. In finance and operations research, this is usually a thing that people talk about exclusively. And beta is a discounting factor. We'll talk about that later. It makes a lot of sense to discount the future. You know, in control applications, you know, this is probably more popular, and the reason is it's tied into stability. In finance, you don't care about stability. I mean, it's true. I mean, you know, in control engineers, you want to keep a plane going forever. You don't want to ever crash. Stability is a huge issue. You want robustness and all this stuff. Would a financial engineer think about robustness when there's only a 10-year time horizon? I mean, it's true. You know, it's not a political statement. It's a fact. It's just a different culture. So discounting is often used, and in that literature, we'd never talk about robustness to modeling error or something like that. Anyway, so this to me is preferred for a lot of reasons, not just mathematical. And again, this is a value function that comes up in average cost, and this is discounted cost. We'll develop that over the next months. Right? Now, I mean, we can kind of guess what this is. Let's forget about this for now. You all know what H is, I guess, by now. I don't know. Well, somebody tell me what I would do if you wanted a representation for H. What's that? Oh yeah, I almost heard what I was thinking, but yeah. What were we saying?
I was just like, what do you mean by a representation?
Well, I want to solve that, you know.
Oh.
You know what I mean? It's not, it looks a little like a generalization of an eigenvector problem. You know, that would be, what's the solution to that if I didn't have the C and the eta? You know? It'd be an well, let's stick to finite state spaces. So then it's an eigenvector equation. And what's the solution? If this wasn't there?
This one, well, for what we've described as P was 1.
Yeah, H would be just a vector with all constant entries. That's right. So it's sort of a generalization of that. And anybody have any thoughts about how they would go about trying to think about what H looks like, what a solution looks like?
I would kind of think like some sort of quadratic, because that's, you know, maybe something similar.
Oh, for particular models, yeah. So I'm not thinking about particular models. You're absolutely right. Like for the linear systems we looked at, if in fact we did solve this. For one, which is Poisson's equation. So for a linear model, well, let me write this, linear state space model. I'll just keep using that, linear state space model, C of x quadratic So we saw that we solved this problem. So go back to your notes. In the special case of a linear system with quadratic cost, we found the solution was quadratic. We also saw last time that for the MM1Q, go back to your notes. Last time we saw the M1Q, if you take C of x equals x, so the buffer size, H was quadratic, not linear. So linear and probably quadratic for that. And that's because Q's aren't as stable as a linear system. They just drift down at a linear rate towards the origin. But that's not, so for particular models, we can solve it. But I'm just trying to think of a general way to get some intuition about what it looks like. You know? And yeah. Oh, I erased it. But if you recall, this thing that's been erased, this bound I had in the average cost, we got that through iteration. You know, remember when we proved the first consequence of the Poisson's inequality, we looked at iterates. You know, and we could do the same thing here. I can look at p squared, multiply both sides by p, do it again, do it again, do it again. So just following last lecture, So this was my starting point last lecture when I said I had an inequality instead of an equality, and I had an eta bar here instead of an eta, and I went through and I just hit both sides by p, did it again, did it again, did it again, and I got exactly this but with an inequality instead of equality. Okay, so you can do the same thing here. Exercise. It'll be on the midterm. Okay, promise. All right. But now I'm not going to say this is greater equal to 0 because it's not. H could be anything. In fact, is H unique? Has to do with your point.
I mean, like if we think about it in terms of eigenvectors, then it is not.
Well, it's not an eigenvector though. So that's not an eigenvector equation. So the argument's slightly different. You know? So the eigenvector equation, I can scale an eigenvector and get another solution. I can't scale H, but I can do something else. Yeah. Anyway, think about it. All right, we'll come back to this. So one of you work it out. All right, one of you who hasn't heard this from me before. But anyway, so I can do this, and immediately I can shuffle things around, and what do I get? Okay, so this term here is a function on the state space. Take it finite if you like. And I'm just, again, being pedantic. You know what I'm saying? Take the function, hit it by p to the k, evaluate it at x. And you can see that, well, is equal to what? It's equal to h of x minus this p to the n, which is also an expectation, right? And then plus an annoying other term, which is this n eta. All right, so we've got h equals something, but let's shuffle this around a bit to make it a little bit nicer. Okay, so let's just make some notation a bit more compact. Let's look at c minus eta. I'm normalizing so that the mean of c is 0. Because eta is going to be the mean of c in steady state. All right? And so what you see here is I've got a sum of c's and an n eta here. I can bring this over to the left-hand side and get a c tilde instead. I wish I'd done that to begin with, but so what? All right? And then this is an expectation. Bring that to the other side as well. And I get a nice representation. Well, all right, that looks pretty good. So what am I going to do now? That's still not satisfying, right? It's not a representation for h. I start with a fixed point equation for h, this or this, and I get another fixed point equation for h. So what would you do? Finite state space Markov chain. Assume it's unit chain, assume it's ergodic. Based on last lecture, what happens if we let n go to infinity with that? Finite state space, unit chain, aperiodic. What does that happen? Yeah, invariant pi of h. All right, so that's one thing I can do. I can just let n go to infinity. But then I get into trouble. I can't let n go to infinity there because I get the expectation of an infinite sum and I go, ugh. So we really have to take the sum outside and then take the limit. Okay. Then you say, well, no, it's still a fixed point equation. Because I've got h equals pi of h. How am I going to solve that? Well, it comes back to my question. Constants don't matter. You know, if I go through and, you know, d times the vector of all 1s is 0. So I can add a constant to my function h and get another solution. All right, so that's a solution, and that's a solution, and I could put anything you want there. You know, so obviously then this must have, if I look at the mean of this, it must be 0 with respect to pi. You know, so this is a solution with pi mean equal to 0. All right, so that's why this is called a relative value function. And the reason for it is because it's relative. You're looking at the cost relative to the steady state. Yeah, that's one reason. All right. All right. Now, another thing you could hope to do again, I need conditions for this. Again, you know. You know, if it's an aperiodic unit chain, finite state space Markov chain, then any solution to Poisson's equation is given by this formula. I just proved it, right? That's completely tight. All right. Now, from a learning perspective, this is an awful representation. If I wanted to use some sort of simulation-based method, I mentioned Q-learning a moment ago, something like that, then this is really unfortunate because a sum of an expectation is really unfortunate. So I would really love to keep this form, you know. And one thing I could do is to say, for large n, that's approximately steady state mean. Let's just say that's an approximation to Poisson's equation. Okay, I'll accept it. You know, and absolutely fine, you can do that. All right. Another thing you can try to do is forget about deterministic times. You know. So let's try to justify this later. But let's suppose we can stick in a random time. So x dot was I called x star x dot my chain that was reachable from any initial condition. You know, so remember under the unit chain condition meant there was some fixed state that I could reach with positive probability from any initial condition. Okay, and so what this is, it's the first time I reach that state. All right, and suppose I can just sort of say, let's just see if we can do it. So instead of putting n there, put a random time. All right, and then I get something really strange. I get an h of x of tau. And what's that? So yeah, so I'm looking at all t for which x of t equals this x dot. And I'm looking at the smallest one, but every t in this min satisfies xt equals x dot.
Should that be lowercase x in h?
Now this is the Markov chain. I'm trying to make this as big as I can. You know.
Oh no, but an argument in h.
Wait. Oh yeah. It's so hard to do it. Yeah. Oh, I mean, yeah. So I mean, these are all up, you know. I try to make it really squiggly when it's a lowercase. You know. Yeah. So this is so I take the Markov chain, which is a function of discrete time, but I plug in a random time, right? But that random time has the property that the process is this fixed state at that time. Isn't that cute?
So if you take out the expectancy.
Well, yeah, so this just becomes x dot. You know, so it's non-random. You know, so this is random as anything, and xt is random as anything, but x tau is deterministic. And so this whole thing comes outside. So that's quite adorable as well. And the same sort of argument. It looks like a fixed point equation, but big deal, that's a constant. And adding a constant doesn't change anything. So this, you know, is also a solution to Poisson's equation. You know, this function of x. So I look at the total relative cost up until I hit this particular state. You know, and that's it. So this required aperiodicity, and this does not. So it turns out this is generally going to be true. So for if you have under the unit chain condition, you need to be able to reach the state. This representation is correct. It doesn't require any conditions, and this is nicer than this one for Monte Carlo methods. Because you're saying my value function is an expectation of a random variable. And so that's how you can end up using simulation-based methods to approximate h. You know, so I have some sort of basis of a function class, and I want to try to approximate this function of h. When I have a representation like that, I can use that information. So it's valuable. All right. You buy it? Yeah. Okay. So partly I want you to see these two absolutely fundamental, you know, these are the two representations that are really most important, and then we have to justify this for sure. This we justified last lecture. That's done. Yeah, and yeah, I mean, really, for a finite state space, you just say, hey, let's take this as a definition, and then do a lot of work, and show it does satisfy this equation. You know, and so you don't really have to justify. You just say, here's a definition, and let's check. But you can imagine it's hard to hit this by p, right? Can you imagine any of you just having the nerve to hit this by p, this function of x? You know, you weren't too scared when I hit p by x squared for an MM1Q or a quadratic for a linear system, but hitting this by p, you know, ph, where this is h, you know, if it doesn't intimidate you, you're a liar. If you say that to me, I mean, if you haven't taken it, you know, you haven't played with this before. Right. So it's really useful to know that it's not actually a big deal to take functions like this and hit them with a transition matrix, because they're actually really easy to play with, you know. Yeah. So now we're going to do it all. We're going to develop martingale theory, strong Markov property, everything, all at once in the next 10 minutes.
So we basically just put an expected value around saying that each just cancels C and cancels eta. It's a constant.
No, right there. Now take a look. Because I've got H of, this was always true. The only thing weird I did was I replaced n with, instead of a deterministic time, I made it random. That's all I did. And the reason I need to talk about martingales is to justify that step. So the reason I can replace a deterministic time by a random time is because of this martingale property. But you had a different point, maybe.
I was just saying that it's kind of funny how the solution was like, what you have in the big box is like expected value of C tilde, which literally just kind of cancels out C and eta.
No, it doesn't though, because eta is the steady state mean of C. You know, eta is equal to the summation over x of pi of x C of x. I know what you're saying. You know, so they, well, I mean, you're absolutely right. I mean, the reason this exists is because asymptotically these cancel out. Yeah, asymptotically, that's, yeah, exactly. And that's why you have to look at a relative value function. Without the tilde, this would be ridiculous. It would be infinity if c is non-negative. Yeah, so you're right. Yep.
How would you know what the mean would be?
Yeah. Well, basically, I mean, in real life, you know, we take averages. I mean, we basically we take samples of the Markov chain and use the law of large numbers. And that's it. You know, I mean, in almost all cases that you care about, P is too complex to solve anything. You know, so that's why we need approximation methods. You know, I mean, yeah. I mean, you know, this, we'll come back to that. But P, even in a finite state space, the state, there's so many states. I mean, you know, I guess the state space for tic-tac-toe is finite, but I've never tried to count it, you know. Yeah. Okay, does that answer? Yeah. Yeah.
Did you say the solutions to Poisson's equation are the same if the adders?
Yeah, adding a constant doesn't matter. I mean, this function of x is a solution to Poisson's equation. You know, because I can just throw away that constant. It doesn't matter. And here I could just throw away that constant. That's another solution. Yeah. So, how am I going to do this? So, yeah.
I'm just not sure. Like, so x dot can be like what is x dot? Like, I mean, why
It was part of the unit chain definition. So any state that I can reach with positive probability from any initial condition.
So it can be any state.
Yeah,
in the state.
that's right. Yeah, that just shows how many there are, because you know, because this function this depends on which guy I chose. Yeah.
So in that sense, h is not unique. So like.
Yeah, I mean. Yeah, I mean, h is not because you can add a constant. We answered our question.
The x dot only affects the constant that we're adding over x.
Yeah, it only affects the constant. Yeah, because if that's the thing, under this unit, actually we've really proved this now, because we said if this holds, then that is a solution, all right? But once we justify this, we say, well, that is a solution too. And we find that you know, any solution just differs by a constant, you know. Yeah.
The way that we define tau as being the minimum t that makes the chain reach that s dot, then that would affect the second part, right? Because our sum is going from t equals 0 to tau minus 1.
Absolutely, it does. You can see.
X dot does.
You can see. Well, this. You know, h depends on x, and so this depends on x dot. So clearly, this does as well.
Yeah. But before, I think it would sit around that shouldn't have an effect on the other thing.
Yeah, I guess it does.
No,
it's hard to say like different tau for different x dots.
Yeah. I mean, maybe I should have put an x. I was trying to leave out save chalk, and I could have emphasized that this depends on x dot. Yeah, it depends on. Of course, it depends on. Tau depends on x dot. I was just saving chalk. See how I'm waiting out. Okay. Actually, before covering all this material, let's look at an application of that for the fun of it. I just believe that's true. So, all right, you're forcing me to do it. You can see why I don't want to, but I'll put it in. So what I'm doing is I'm getting rid of the tilde, I'm expanding that out because I want just to see this, you know, very clearly. I'm conditioning again on x equals x. I'm just saying in huge font that I'm starting out at initial condition x. And what is this equal to?
H of x.
No.
H of x minus.
All right. So what would happen if I put in a bullet there? So what if I look at the special case that I start at the regeneration state, if you like. So I start at the special state, and I wait until I return.
U is 0, right?
Yeah. Isn't that cool? All right. And that's equal to the expectation of the sum t equals 0 to tau minus 1 of c of xk. And you can see I just don't want to have to keep on emphasizing this dependency, so I'll just write tau again. Minus eta times what? Well, yeah. Hold on.
So the reason why that's 0 is because by starting at x dot, you're letting tau be 0.
No. That's why I was so careful to make a 1 there.
Is it because you
No, 1, 1, 1.
The definition of h of x is that's h of x. So whenever you put
Like-
x dot, x0 equals x dot, then that becomes h of x dot.
No, that's clear. No, just that I want you all to see there's a 1 there. So, you know, the tau is equal to 1. That was the question. So, yeah, there is sometimes you write tau equal to 0 for other devious purposes. But yeah, I was very careful to, yeah. So I start there, and it might be true the next step I'm still there. Like for an MM1Q, if I start 0, there might not be an arrival. So it is possible this could be 1, you know, but it's greatly equal to 1. All right?
Like saying x dot, like x dot we stay at x dot, right?
No, unit chain, oh no. All these, a Q is unit chain. Any state I can reach with positive probability. Yeah, unit chain is just any countable state space Markov chain you ever come across in an engineering context will be unit chain. I mean, having an absorbing state, like a graveyard state, I get to it, I die, we're not going to look at those except for an analysis. So it just means I can get this positive probability. It doesn't mean I'm stuck. Right? So I take this apart, and this is easy. I took the C and I kept it here. What about this? The sum from 0 to tau minus 1 of a constant. I can just take the constant outside, right? Isn't that lovely? And so what you end up getting is what's called Kack's theorem. So basically, you're looking at you're starting at x dot, you look at the cost up till, but not including the time I get to x dot, and then you're dividing by the total amount of time it took to, that regeneration cycle to take. There's a regeneration cycle. I start x dot, I wait till I return to it, and I might do this over and over again. And so we get a representation for the steady state mean is a sample path ratio, which is also useful. I mean, if I'm claiming that Monte Carlo methods, it's not, when you see an expectation of something, you should say, ooh, I can use simulation techniques. That's a very, very useful representation. Yeah.
So how would you take the expectation of the time? Isn't that just some constant? You're saying that you would run it?
Yeah, I'll do a simulation.
And then
Yeah.
that with the average.
Yeah, so this is a really nice, reliable way, if you're scared, to estimate eta, is to just keep on taking samples of this, and samples of tau from observations of the Markov chain, and then you have a estimate of this, and divide. You know, if you're scared of, you know, and that's, I mean, it's much easier to understand than the other techniques I'll be presenting to you. We're going to build a lot of ways of estimating this baby, because once you understand how to estimate this well, then estimating this well is a minor extension. Yeah. Yeah.
So this only applies to a finite state space?
Well, what's amazing, I mean, so countable state space, but then you have to know this is finite.
You have to know that
these are both finite. And for general state spaces, believe it or not, even like when you have densities, there's a generalization of this. It's amazing. And that's Newman, 1984. You know, just when I was doing my PhD thesis, and the book was too impenetrable for me to read, but he has a generalization of this he discovered in the late 70s, in 78. And it's not hitting a point, obviously, because you've got densities, but he has a magical way of regenerating as if you hit a point. He actually constructs a point on a new state space. It's wild. I mean, you wouldn't believe it, you know. So that's why I didn't believe it as a grad student when I saw this result. I just closed the book, put it back on the shelf, and I didn't look at it again until I was an old professor. So yeah, so there are generalizations. Keck's theorem is really universal. You know, it's and you can see we recovered sort of the thing we saw before. I mean, if instead of, well, forget it. Never mind. That's that. It's funny. What time is it? 2:40. So
So
yes.
when you say we're assuming tau minus 1 is finite, it means that the chain would be such that it would return to x dot at some point.
Yeah. Well, yeah. 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 We have to justify why. We have to justify why this is finite, but we'll see. It's obvious.
Okay.
We'll explain that.
So if something is recurrent, would that guarantee that it's finite?
Well, that's we haven't defined all this stuff yet. That's, you know, we've got some work to do to explain how would you define recurrence? Yeah, it's okay.
Every state.
No, not every state. See, never needed every state here, but. Well,
my definition.
Okay. Well, here's the definition of recurrence, in fact. Too many words for me to take in. There's only a few more minutes left. All right, so actually, I mean, so the tau is the same. I'm sorry, it's just, you can see it's hard to write double subscripts, okay? The tau is the same definition I made here. So a Markov chain is recurrent if not, this one, for the unit chain condition said this was positive for every initial condition. Recurrent says this is 1 for every initial condition, and shit. That's actually, actually, that's not true what I just said. Recurrent, you would take x equals x dot. The definition that you'd find in any Markov chain book is it's recurrent if from starting at x dot, the probability of returning to x dot is 1. All right? Harris recurrent is that you reach that state with probably 1 from every initial condition. And we'll stick to that. All models we ever look at will satisfy that. And for a finite state space Markov chain, and again, that's not, I forgot the bullet again. This is, I don't want to get into this. It's too technical. Positive recurrent means starting x dot, the return time has a finite mean. So it means this denominator is finite. All right? And this will turn out to be, for a finite state space Markov chain, this is always true. All right? And we'll see that. It's not hard to show. And in fact, there it is. There's a proof. Actually, I mean, we have a minute, don't we? We have 1 more minute. I'll prove it. It'll take a minute. Be quiet. Unless you have a real question that's a clarification question.
Last thing, doesn't the definition of x dot imply that that will be less than 30?
No, x dot.
Starts at 1.
Right,
Yeah, it starts at 1.
yeah. What? No, the min is t greater equal to 1. Yeah. Okay, so we'll have to give examples, but one more application. And we got to do this since we got all these questions. This was true for any C. Let's plug in a C where we know the numerator. What if C were 0 for every x except for one x, which is x dot? What is the sum then?
1.
It's 1, because we're summing to t minus 1, tau minus 1, and tau was the next time I saw x bullet. So this whole sum reduces to 1.
Well, it's 0.
No, we're starting at 0. See, can you imagine how careful you have to be teaching this course? Because that's got to be greater than 1. That's got to be 0. You got to be so cautious. You know?
Restarted.
It would have been true to sum from 1 to tau, but I would have gotten screwed up. Well, no, I wouldn't have. It would have been fine. But so in that special case, this becomes eta is what? Eta is the mean of C. Well, that's just the mean of this, which is pi of x dot. And how could I think I wasn't going to present that? I mean, and forget the 8 in the middle. Let me just, you know. So the steady state probability of being x dot is 1 over the mean return time. All right? And so that's positive, so that's finite. So every finite state space Markov chain is positive recurrent. Does that answer your question? that was an answer to your question. is that yeah. All right. So I'm not going to try to prove that develop the theorist try Markov property and martingale, but at least we've got some motivation. I mean, this completely requires understanding this. I mean, really, it's even to write it down requires these two things. So we'll do it next time. And I think that's it, right? We're out of time. Yeah. Okay, cool. All right, until then. And I'm trying to get lecture notes cleaned up for you. Maybe the next 24 hours I'll get them on all of this.